Okay, so we've looked at another fractal. We've looked at simple interest, looking at deposit into a bank account and 5% interest every year, and how those can be represented using exponential models. But we've got these 3 tables on our workshop doc this week, and what the heck, Mr. Garlitz, how do we do these? So think back to last week. We had recursive routines. So we had a starting value, and then we had a constant multiplier. So I'm going to go through a few examples here, and maybe that'll kind of set you up for what I'm looking for. So if I look at these tables, first of all, this first example, decimals, scary. So let's skip this one for now. Let's come back after we've kind of got our stride. If I look at this table here, so table 2, we'll come back to table 1, I promise you. But let's make sure we know what we're doing. So 0 corresponds with 4, input 0, output 4, input 1, output 8, input 2, output 16, input 3, output 32. So you might be able to see what the constant multiplier is right away, but we need to know, what are we multiplying by to get from here to here? 4 times something gets us 8. And I'm hoping that right away we see, oh, I'm multiplying by 2. Well, let's see, is that the same from 8 to 16? 8 times 2, yep, that's 16. And so we know what our constant multiplier is. So if this is the case, then I can rewrite this a few different ways. So let's get a new table out. So 0 is our starting value is 4. When I have 1, I'm taking 4 and I'm multiplying it by 2. When I have 2, I'm multiplying that by 2. When I have 3, I'm taking 4 and I'm multiplying it by 2 yet again. And from this point, we see that we've got expanded form. So let's give this a scooch. And then we can see, what does this all mean in exponential form? Let's see if it takes. All right, cool. So in exponential form, 4 times 2, just one time, means that I have 4 times 2 to the first power. 4 times 2 times 2 means I have 4 times 2 to the second power. And I hope you're seeing a pattern by now. What this means is we can go in both directions, right? So 4 is the same as 4 times 2 to the 0 power. Because a property we haven't talked about is that whenever you have a number to a 0 power, that number becomes 1. And I can link in a video into our resources on why that is. But now we've got this relationship. I have my starting value. So if we're thinking recursive, a recursive routine, for example, 2, our starting value, we start with 4, and then our rule is multiply by 2, And what we saw last week is that we can boil this down to a formula, a function. Actually, let's call this a function instead of y. So f of x, which is the same as y, is equal to a, our starting value, times b, our multiplier, to the x power. So I know that my starting value is 4. So I'm going to replace a with 4. And I know that my multiplier is 2. So I'm going to replace that with 2. So now I've got this function, 4 times 2 to the x power. So let's just double check this in Desmos. Let's put our table in, table of values. So I have 0, 1, 2, and 3, right? We started with 4, we went to 8, 16, 32. And then I want to make sure that I have this function y equals 4 times 2 to the x power. And it's already looking like a success. So if I close this up, and then let's squish this view a little bit so that we can see it a little bit better. So 0, we only went up to 3, so let's do that, and then 0 to 40, I guess. And if we zoom out now, we have a better perspective. Here are our values. We're doubling every time. All right, let's take a look at another example really quick. We can start to see what some of these are, right? So I don't know that I necessarily need to go over example 3 and 4 because you can see what's happening here. So example 3, it looks like we're multiplying by a half, multiplying by a half, multiplying by a half. Okay, so if that's the case, I know what my constant multiplier is by looking at that table. So if I go to 3, I can go right to my starting value, which is 4. Let's just call that starting value is 4. And then our multiplier is 1/2. So I can write a function 4 times 1/2 to the x power. And I've created an exponential function for 3. If I go to example 4, my starting value, whoops, too far, is 2 because it corresponds with my x value of 0. And it looks like I'm multiplying by 4 every time. So once again, starting value is 2, multiplier by 4. So now that I've got a starting value, I can write, let's actually call this one, let's call this g of x, call this h of x. The name really doesn't matter, just as long as we have it in function notation. So 2 times 4 to the x power. Okay, well, Mr. Garlitz, that's all great, but what if we don't know how to find our constant multiplier? Like, what if it doesn't look that easy like it did in example 2, 3, and 4? All right, so let's take a look at example 1. So in the case that you don't know what your constant multiplier is off the bat, what you can do is create a simple equation to help you find it out. So if I've got a starting value of 2, I'm multiplying that by some value. Let's call that value m for multiplier. So 2 times m is going to give me 0.5. So now this is a very simple equation that we did like way back in the fall. So to solve this, I want to figure out what the multiplier is. So I need to isolate that. So I'm going to divide both sides by 2. These cancel, and I'm left with m equals, our multiplier equals 0.5 divided by 2. If you're not comfortable with that division, let's go to Desmos, calculator of some sorts. Turn these off for a second. 0.5 divided by 2, 0.25. So from here, I see that to get from my first term to my second term, I multiply by 0.25. Let's see if that's the same case for the next. So I'm going to create a table. I'm going to do example 1 in this table. So 0, 2, 1.5. 2 should be 0.5 times 0.25. Let's just make sure that that's what we want. All right, so it looks like the table here rounded down actually. So if we do have a constant multiplier of 0.25, and then for 3, we should get 0.125 times 0.25. And then we see that we're getting all those there. And this is a decreasing, right? These values are going down. 125 times 0.25, so 0.03, and they rounded once again. We can be more exact with Desmos. So if we go back here, I'm going to zoom in so that this shows a little bit better. Our y value, well, let's go with our x value, 0 to, let's say, 10. Our y value doesn't really get above 2, so I'm going to just say 4, and whoops. Let's say negative 3 to 3. There we go. So starting value, and then we're decreasing. We know our multiplier. We know our starting value. So I can write a exponential function, right? So starting value is 2. Multiplier is 0.25. So I can write an exponential function. Let's get rid of some of this math. Whoops. Okay, come on. And I can write y, well, let's call this one, what do we do, f, g, h, let's call this k of x is equal to starting value times 0.25 to the x power. And this will help us find any other value. And if we go back to Desmos and we put that function into there, we should see it coincide with all of our data points. K of x equals starting value of 2 times 0.25, whoops, to the x power. And there we go. So that looks great. Now, what's great is now that we have it in function form, let's say I wanted to know, well, what's my value when I'm on step 40? Step 40. And it gives me this very, very, very small number. Let's just go to step 10. A very small number so that it doesn't give us scientific notation. But I'm hoping this helped guide you through what do you do when you have an uncomfortable set of data and you know that it's got an exponential pattern to it.